previous class. So this why data profiling is a very important library which you should remember, and this should be the first step while acquiring. After you have acquired the data, you should look at these graphs and then plan your pre-processing activities. Now, keeping that aside, we will start with machine learning, right? I mean, supervised and unsupervised machine learning. Now, before that, there is linear regression. Okay. So, what is machine learning, right? So, essentially, generally in code, what we do is in programs, what we have is we have inputs and we write code which produces outputs, right? This is general programming technique, right? We have a code, and into that code we provide some input, like for example factorial of a number, right? You give the number, the program runs and produces the factorial of that number. Now in machine learning, what you do is you give inputs and outputs and let it learn the code. You don't write any code for them, you only give them, I mean, you write the code for them to learn, but what essentially it is learning is the code or the relationship between input and output. Now what this code was doing in general programming is it was establishing a relationship between input and output via this code. Now here you just say that, okay, I don't know how this output is generated, but I have some inputs and outputs. Can you learn the code? Or can you learn the relationship between them? The code essentially is the relationship between input and output. So this is what machine learning is. It learns from the input and outputs, not the correlation, the relationship among them, right? And this is what is machine learning. Machine learns relationships between input and output. Specifically talking for supervised models. In unsupervised models, you don't have outputs, you have only input. It learns from inputs only. But in general, machine learning is the concept where machine learns from past historical data or past experiences, right? So that is machine learning. Now, what is the difference between traditional programming and machine learning? We discussed. In traditional programming, we have input, we write code to produce output. In machine learning, we have inputs and output, and we learn the code using machine learning. I mean, the code or the relationship between input and output is learned using machine learning. Second is phases in machine learning. So phases in machine learning, we have discussed previously. There is data collection, data wrangling, analysis of data, training the algorithm, testing the algorithm, and deploying the model. Right? Now, phases and steps. So essentially, these are the same thing. Phases in machine learning and steps in machine learning. These are the same thing. Now, what are the different types of variables, right? So there are independent variables which are called inputs, and dependent variable which are called labeled data or the output. Like for example, in our house price prediction, we have number of bedrooms, price per square feet, area. All these are inputs. What is the output or the dependent variable? Dependent variable is what is the price of the house. Price per square feet is not the dependent variable. Price is the actual price of the house, right? So these are called dependent and independent variables, and these are important terms. Now, machine learning types, right? Supervised machine learning models, unsupervised, and reinforcement machine learning models. Now, supervised machine learning models are where both inputs and outputs are given, and these are task driven. Like for example, you want to predict house price, you want to see whether some person has cancer or not. So this is a task. There is a task that you want to, or there is a goal that you want to cater to, right? So that is a task driven application, which is a supervised model. Now, unsupervised model is a data driven application. So you have a lot of data and you want to derive insights out of those data. So then you say that is an unsupervised machine learning model, where only input is there, no outputs. You are given you throw some data at a machine learning algorithm and you ask it to categorize it, recommend something, and so on, right? So these are unsupervised models. Reinforcement machine learning. What is reinforcement machine learning? Is the learning process in which machine learns by making mistakes. So it is similar to how humans do, right? So in our childhood, we knew that, okay, in the classroom, if we shout or if we make too much noise, the teacher hits you. So that hit is like a punishment. So it's a punishment and reward system. Whereas if you study well, stay silent in the class, you are appreciated. That appreciation is a reward, and that hit you get, or that punishment that you get from teacher, that is a punishment. I mean, the kind of let's say if in front of many people someone insults you, so that is like a punishment. So we now when we get reward, we are encouraged to do the same thing again and again. When we get a punishment, we try to avoid those things. So the same concept is used in reinforcement learning, similar to how human do in real life. So when the algorithm is doing good, you give it more points. When the algorithm does something wrong, you give it negative points, so that it understands that okay, if I am doing these things, I am getting negative points, and my goal is to maximize the number of points that I have. So I will do only the things for which I will get positive points. So it will gradually learn. It will keep on doing negative things, I mean get minus points, and it will keep on learning that okay, this action should be avoided. Next it does again something, and again if it gets minus, it says okay, this action also should be avoided. Again it does something for which it gets positive, it reinforces. So that is why the name is reinforcement learning. Reinforce the action based on reward or punishment. Right? So these are the three kinds of machine learning approaches. Now within supervised learning also there are two categories: regression and classification. So relationship between two or more variables, those are continuous variables. So essentially the output, essentially here what I mean is output is a continuous variable, right? So if the output is a continuous variable, so what it means is output is not discrete. Like for example, house price. House price can be anything from 10 lakhs to 1 crore, more than that, maybe 10 crores, 20 crores, anything, right? 30 crores. So it can be any number between that. So there are too many possibilities. When there are too many possibilities, then it cannot be a categorical thing. Categorical variables are those where you have limited number of things. At max, let's say 25, 30, 100, maximum 500. Till that you can say okay, it is a categorical variable. If it is beyond that, if it has more than 1000 possible values it can take up, then it cannot be. In fact, it is not even 500. At max I think 50. Till 50, 60 we call it a categorical thing. Otherwise it is a continuous variable or a nominal variable. Okay. Now categorical variables are something like yes, no, true, false, 0, 1. It can also be numbers from like 1 to 10, something like that. It can be like names of states in India. So these are also categorical variables. So these are where the output or the dependent variable that we talked about here is a categorical variable. Then the problem is a classification problem. We are classifying into categories, and the other one is a regression problem. Now in unsupervised learnings, what we have is clustering. Clustering is like grouping of different data blocks into a single bucket, that is called clustering. In other ways, association, where we compare two groups of things, so this is called association. And then we have recommendation. So recommendation is suggestion based on some data. Like for example, you are looking someone is watching Netflix, and the kind of movies or the drama someone likes to watch. Based on that, it recommends by using user profiling. Essentially it profiles your way of watching and finds out other users who are like you and what they watch, and based on that it recommends you. We will see in our subsequent session how to build such a recommendation system also, which is called collaborative filtering recommendation. So essentially these are supervised, these are unsupervised, and we will use mostly scikit-learn for this, for model creation. Now looking at, so we'll start today with supervised machine learning. Okay. Now supervised machine learning is, we said, both input and output are given, and we will start, to be very precise, we will start with regression. We will look at classification some other time. I mean some other time in the sense in the next session mostly. So
Okay.
today we'll focus primarily on regression, and we are looking at scikit-learn library, which you have already seen in the previous classes also. And so what it does is, I mean, what we do is this is an equation of a line, right? Y is equal to mx plus c,
Huh.
where mx is the slope, m is the slope, and c is the intercept, right? Uh, so these are some rules which we will discuss later. What I will tell you is, let's say we have this kind of a sample problem. Okay, we have two variables, area and price. Now, based on area, this price is changing. I mean, area of the flat. Only one
Right.
variable. We are looking at, for simplicity, we'll start with single variable. We'll look at multivariable later, right? So we have one independent variable which is area and one dependent variable which is price. What is the problem statement? Giving the data, build a machine learning model that can predict prices based on square feet area. Right, so you want to give area, square feet area of a house, and you want to predict the price. Okay. Now, if we look at, let's say these are the x-axis is area and y-axis is price. Each of these blocks represent the price, right? So let's say 2600, if it is a square feet, the price is like 55 lakhs or something. If it is 30,000, it is like 57 lakhs or 55, 56 lakhs. If it is 3200, then it is like 60 lakhs or more than 60 lakhs, slightly more than 60 lakhs. Now, the goal of a machine learning model is, I mean, at least linear regression that we are talking about. There are other algorithms. We'll start with linear regression, which is a simplistic regression model. What it tries to do is, if there are some variables, it will try to draw a line so that these gaps are minimized. It will try to create a line which passes through all the points, but that may not be
Yes.
possible because all the points may not be in the same line, right? So you will try to find the best line which is as close as possible to all the points. Now, to do this, what happens is, for each of the point we do a projection to this line, which is called the distance from this line, each of these points, and we try to minimize this thing. So this is the distance, let's say delta 1, delta 2, delta 3, delta 4, delta 5. The goal is to minimize this delta square of delta. So this is a summation. We want to minimize this delta. That is the objective of the machine learning regression model. Now, if we look at the line, what would be the line? Home price is equal to m into area plus b, right? This is the line that we will need to learn.
Yes.
Now here, what is m? M is the slope of the line, which is tan theta of this, and then this b is the intercept, like where this line is intersecting the y-axis. Here b is 1, and slope. I mean, we have to find tan theta. We cannot be determined here. It looks like it will be somewhere like 45 degree. It looks like 45 degree. So like tan theta will be 1, like something like 1. Okay, so this is a general line equation. It is called slope or gradient, and the other is called the y-intercept, right? Where the line intersects the y-axis.
Yeah. Hello.
Yeah, tell me.
You Purneni, did you start a recording?
Yes, it is recording.
Okay. Sorry.
Yeah, I've started at the beginning itself. Okay. Now, uh, what we want to do is, we want to learn this line, right? Till this, I hope it is clear. We want to learn a line
Yes.
which, given an area, tries to predict the price, right? Now we know that the line equation is y is equal to mx plus c. Y is our independent variable, which is price. The dependent variable is x, which is area, and b is the y-intercept, which is like a regularization term, right? Now we will import all the libraries that are required. Like pandas, we need scikit-learn, and we need matplotlib. Okay, I will just run this, execute this. It's done, and we will load this data set, home prices 1.csv. It has uh, it has two columns, area and price, and it has only few rows. I mean, I think 4-5 rows it has. Let me check home prices one. Yes, see, it has a very small data set with 4-5 rows. Okay. Now, here we want to understand if there are any null values or something. To do this, you just write dataframe.isNull.sum. So it will tell that for each feature or each column value, whether there are any missing values or not. it says 0, which means there are no missing values, so we don't have to do any missing value handling as such right now. Okay, now what we do is, as part of exploratory data analysis, we will try to plot the graph. So scatter plot we talked about, PLT is coming from matplotlib, and we're doing plt.scatter. We are passing the x value, which is area, y value, which is price. We are saying color is red and marker is plus, right? So with this, and we are just running this, right? So if we run this, this plot is getting generated, and it is pointing out all these things. So if you see, there are many lines that are possible. I can draw a line like this on top, on like a horizontal line. I can draw a line like this. I can draw a line like this. I can draw a line like this, and so on. There are many possible lines that you can draw here. But what machine learning algorithm helps you is to find the best line, which will go as close to the line as possible, the closest line, with least, which minimizes this function, which minimizes this one, minimizes the delta square, sum of delta square. Now we have plotted this. Now what we will do is, from this, now we have this data set, right, which is in this data frame. We need to split it into two variables, dependent and independent variables. So x is the dependent variable. Let me call it capital X. Capital X is actually the better notation. What we are saying is df dot drop price axis equal to columns. So after dropping price, whatever is remaining is the data frame will be assigned to x, which is the area, right? So area is our dependent variable. We have set this here, and next is data frame dot price, which is the y value, which we have set to this, right? So now we have x and we have y. X is the area, y is the price. Now what we will do is, we will do from, what we have done is, we have imported scikit-learn linear model, right? So from linear model we will create a linear regression model. So this line of code is creating a empty model. It has not learnt anything right now. It is a blank model which is there, which is set to this variable regression. Now on this you call fit, reg.fit, and you pass your x and y. Now if you pass your x and y, this is where the model will be trained, right? So now once this model is trained, now after executing this line, whatever value is there in your reg parameter or variable, that is actually your learnt model. Now if I want to do some prediction for 3300 square feet, which is not there in this data set, right? 33,000 is there, 3,200 is there, 3,600 is there, but 3,300 is not there, right? So if I want to do this, what I need to call is, I have to call reg.predict and pass 3,300 like this, right? And if I just run this, it is giving you this value, like 62 lakh something, point something. So around 62 lakh would be the price for if your square foot area is this. So this is how you can predict some new value using by calling the predict function on your learned model. Now I talked about a line, right? This reg is nothing but a line. So you can check your coefficient, which is your intercept, right? So this is actually the intercept. So using reg.cof underscore, you will get your intercept, which is 135 point something. You sorry, this is your slope. Sorry, my mistake. So this is your slope, and then this is your intercept. So intercept is this much, slope is 135. Now if you see, what we predicted for 3800 is like 62 lakhs. Let us apply the same y is equal to mx plus b that we started off with, right? So if we apply y is equal to mx plus b, what is m? M is the coefficient, which is 135 point something, and a square foot area is 3300, and this is your intercept. If I just run this code, you will see it is getting the same value, right? Same value as this one, right? Both of them are same. So what it means is, this reg model predict is nothing but a line equation that it is storing internally. Now same prediction on other data, like 5000 square feet also you can run it, and again do the same thing, slope and intercept, and you will see that both of them have same value. Now the last thing is, sorry, okay, x is not defined, it's capital X. Now you want to see how well the model is learned, right? So if you just do reg.score and pass x comma y, it will return you a R2 score. What is R2 score? I will explain later when we talk about how to evaluate your models. I mean, once you have learned, once we discuss all the regression and classification model, I will take one session specifically for evaluating the models. Because let's say you have learned a model, how do you evaluate whether your model is learned properly or not, right? So for that I will take a session which in detail will talk about what this scoring function is, but R2 score is. But for the timing, you remember that reg.score will return you a score R2 score which will be between 0 and 1, and the higher the value, the better the model is learned, right? So here
Yes.
0.95 is like a good model. More than 80% is usually, depending on the use case, but most of the time a score of more than 0.8 is a good score. Okay. Now this is what we saw for linear regression in
Regression.
one variable. Only one dependent variable we have. Let us now see the same thing, because house price is not only dependent on area. There are other features, right? So let us see a little more complex thing, like where we have area, bedroom, age and price, right? So here sample problem for predicting house price in New Jersey. So here the equation will change a little bit, right? So how the equation will now become? The equation will now be, previously it was price equal to m into area plus b. Now the equation will become price equal to m1 into area plus m2 into bedroom plus m3 into age plus b, right? Because now we have more dependent variables, area, bedroom and age, which essentially decide what should be the price, not only the area, right? Process is exactly the same, the approach is same, only thing is that now you have more variables. So it is actually also a line equation, but this line equation is in more dimension. We saw in this thing a simple line because it is in 2 dimension, right? Area versus price. But now if you have 4 dimensions, like area versus area plus bedroom plus something else was there, na? Area plus bedroom
Square.
plus age, right? Age, I mean how old the house is, right? So area, age plus bedroom, if you take all of them, you cannot create a plot like that, right? I mean you can at max create a 3D plot using MATLAB or something, but in fact in this also Matplotlib also 3D plots are possible, but beyond 3D you cannot plot anything, right? I mean 4 dimension, 5 dimension, how do you plot? You cannot do, right? So in that case what you have to do is, for each of these parameter against price you can create a graph and try to analyze, but all of them together you cannot create. Now but what it is doing is, what that that is a limitation for visualization. I mean we cannot visualize it, that line properly, but that line does exist actually, and that line equation is given by this line. This is actually a line, but this is a line in a higher dimension which we cannot see in a plot, because we can only see at max 2 dimension or 3 dimension. That is the thing,
Yes.
right? So that is why, but this line equation is always a valid equation. This is a line equation. Now same as previously, these x1, x2, x3 are features, or these are many names, right? Inputs, you can call them inputs, you can call them dependent variables, you can call them features, right? All of them refer to the same thing. Now y is called the target, y is sometimes called the output, or it is sometimes called the independent variable. Target, independent variable, and the goal, these all refer to the or the dependent variable also. Dependent variable, target, goal, so these are called y, right? So these are synonymous names. Similar approach, same code, no change in the code. You will see you'll see we are doing the same thing, matplotlib. Now we are taking this sorry, I haven't imported this. Now you'll see this is the data frame now. Now here if we look at this thing, same thing, you'll see there is a missing value in bedroom. We also saw this thing here, right? In this alerts
Ah.
when I showed you that this has a missing value, it was saying something. Bedroom has one missing value. So here using code also it is saying bedroom has one missing value. Now but without without filling these missing values, you cannot directly give it to machine learning model, right? It will fail. I mean, it cannot work on something which is not a number, right? So you have to fill it with something. So for this, there are many approaches, right? So I told you in the previous sessions also, if it is a categorical value, we replace it with mean or median. Sorry, if it's a numerical value, we replace it with mean or median. If it is a categorical value, we replace it with mode, right? Now, number of bedrooms is a categorical feature. It is not a numerical feature, because number of rooms can be limited, right? 2, 3, 4, 5, 6 at max. 2 bedroom, 3 bedroom, 5 bedroom at max, not beyond that. So it is a categorical variable. To impute this value, to replace this missing value, which is this one, what we need to do is we do a df.bedrooms.mode, right? So, and we get 0. So like and then we'll get the mode, which is like 3, right? If you run this code, it will say the number of mode of this is 3, because most of the rooms here are 3. You'll see this one is 3, this one is 3,
Yes.
and we have 1 4 1 5 1 6, right? So that is why 3 is the maximum. So we get mode as 3, and we set this. We use df.bedroom.fill_na. Fill na means fill anything that is not. Na means not a number. So fill na is replaced with, I mean, we use mode to fill this thing. Now you'll see that this data frame gets filled with, this value is getting filled with 3. This one was na previously, right? Nn. Now again, if we do the same thing, sum, you'll see no missing values. Now we are ready. We can do some further analysis in terms of df.info to understand the kind of data types we have. Like for example, you see bedroom is a float. These are integers, although you don't need this to be float. So if you want something, like if you want to change this, what we can do is we can say df.bedrooms.asType int. If you do this, it will convert it into integers. Bedrooms equal to, okay. If I do this and again print the df.info, or maybe df.info, df.info, see, everything is now integer, right? So now it converted this into int32. If you want int64, maybe I'll have to do int64 here. Let me see. No, int64 is not there. There must be something. I will have to look. But this is how you convert. Because this is coming as int32, right? All others are int64. What it means is these are 64 bits integers. This is a 32-bit integer. Although 32-bit integer is also fine, because 32-bit integer can hold numbers up to, let's say, 2 lakh or 3 lakh, and we have rooms at max, let's say 2 or 3 or 4 or 5, right? Which is fine. But if you want to convert this into int64 also, I don't know what it would be right now, but there must be something. We can quickly check also. Let me check otherwise. Convert int32 to int64 in Python. As type np dot, okay, np dot int32, okay. So there is np dot int64, let's say. We try. np is not defined, okay. Let's do import numpy as np. See, now everything is int64.
Yes.
Right? So int was also fine. That was not a problem. We could have just written int also. That is okay. So this is how you do a info and check what are the data types. Like for example, if there were any string values or something, no, so then that column will show as object. So then you understand, okay, this is a category. Or sometimes you just by looking at the data frame, you want to quickly understand how many categorical columns I have, how many numerical columns I have, and so on, right? So if there are some values, some columns which the type is coming as object or string, then you know that, okay, these are categorical columns. Okay. Now again, similar to the previous approach, same thing we are doing. X we are dropping the price column, and whatever else is remaining is X, which is like area, bedroom, and this thing, and then price is df.price, which is the last column. and same linear model dot linear regression, we are passing x and y, right? So we have learned a model. Again, if you look at coefficient here, you will get 3 coefficients. There we were getting 1 coefficient. Here getting 3 coefficient. Why? Because the equation of the line is m1, m2 and m3. So you will get m1, you will get m2, and you will get m3. So you will get each m for each feature. So that we have 3 features. So we'll get 3 values of m here. Where is it? 3 values of m here. 1, 2 and 3. This is m1, this is m2, this is m3. Intercept is this one, which is this. And again, if we do a predict some value, we'll have to pass 3 values now, because predict now takes 3 things. There it was only taking area. Here it is taking 3 area, number of bedrooms, and what is the age of the flat, right? So if I just run this, you will see 48 lakhs is the price. You can do the manual calculation also, which is like m1 into x1, m2 into x2, and m3 into x3. So you got this, right? M1, M2 and M3 are coming from here.
Yes.
X1 and X2 and X3 are coming from our inputs, and we run this and you will see the same value as this one. I mean, where is it? This,
Yeah.
this one, right? This one and this one are same. Okay. So yeah, so this is a general supervised learning in using linear regression. Same approach can be done with multiple models. Today we only focus on linear regression. In the next class we will see what are the different models, a detailed categorization of different model. Linear regression is the simplest model, okay, and that is only for regression, not for classification. For classification, we have other classification models. We'll look at a similar problem like this for classification in the next session. And once this regression and classification are done, we'll go deeper into what are the other algorithms are there. I mean, linear regression is the starting point, of course. But what other algorithms? There are algorithms like decision tree. There are algorithms like random forest. There are algorithms like support vector machines. There are algorithms like multi-layer perceptron. And then what are the problems with this model which deep learning solves? So those kind of things we will gradually look at. But here also there are few other things like model evaluation, how to evaluate the model. Right now we only use score, which is like for, see here also we can do that thing, right? So score, reg dot score, and you pass x and y. So reg.
Right.
So it is like same around 95 point something.
Yes.
So so which is a good decent model, but you have to remember that this score is on your training data. For test data there will be 2 kinds of score. One is what so on training data it is very usually you will get good numbers in terms of score. The challenge is to get a good score on test data. What do you mean by train and test data? Let me try to explain that to you. Okay, now what we have said is we have all this data, like these 5 data points are there. All this data I am giving this model all the data to learn from, right? So it is taking all this data and learning. Now then what is the concept of train data and test data? So all this data that you have given to the model, to the fit function, essentially to this fit function, right? We are calling a fit here, right? This fit is the function where the model is actually getting trained or model is learning. So this fit function is taking this entire data set. So whatever x and y you pass to this fit function is called the training data. Now if I have some more data on which the model has not seen or model has not worked on, right? So like for example, I know that for 4,500 the price will be 45 lakhs, let's say. So this is a data which is not there in the training data set. Here there is nothing called as 4,500, but I know this data. This is a valid data. So otherwise the other option is, if you don't have any such other data, what you can do is you can split this data into 2 parts. So let's say I use row number 0, 1, 2, 3 for training. I keep 4 and 5 for testing, whether the model is learned properly or not. So that is called a train test split. Okay, there is a function in scikit-learn, train test split function. So let me quickly take this one, take this code and put it at the end. Okay. So this is an important concept of splitting the training and test data. Okay. This is not splitting. Where is the splitting happening? Test size, this one. Okay. So this X and Y we already have. Okay. So here, let's say we have X as this, right? Now this X actually, if you do a type of X, it is showing as a data frame, right? So it is a data frame. If you want to convert this X into a NumPy array, what you have to do is you have to call X dot values. So this is, you'll see, it is now an array. If I do type of X dot values, it will be a NP array. Okay, it is a ND array, which is NumPy ND array, right? So now you can now to this function you can either pass your data frame or you can pass a NP array. Anything is fine. Now what we are doing is we have X, we have Y, we have a test cycle. Let's say I want to use 20% of my data for testing and the remaining for training, right? So if I do this and run this code, and if I just now look at xtrain, you'll see it has this thing. I mean, it has 4 rows, right? So why it is shuffled is because shuffle is by default true. If I just run this, you'll see random state, training size, shuffle is by default true. If you want to set shuffle as false, you have to pass this equal to false. If I say shuffle will be false, then it will, what happened? Okay, so you'll see it is sequentially 0 1 2 3. But if I say shuffle true, it will take any random 4 out of this. Now how many rows did we have? We have 0 to 5, like 6 rows, right? So 20% of 6 is how much? 20% of 6 is 1.2. Like, so it will round that 1.2 to 1, sorry 60% of 1.2, and it will try to seal it. I mean, it usually does the upper bounding. It doesn't round it to the lower number. It will always do a upper bounding, because you cannot have 1.2 rows, right? You can either have 1 row or 2 rows. Usually when doing this, when we pass 20% or 0.2, which is like 20%, it will do 1.2 and it will take the 20% of the, I mean 1.2 means 2 rows. So 2 rows will be there in test and 4 rows will be there in the training. Now let's say out of 6, let's say I do 50%, right? 50% I want to keep as training and 50% as testing, which is not actually a correct thing to do. You see it is coming down to 3, right? 3 rows. Because I have set shuffle as true, if I do shuffle as false, it will be first 3 rows, right? So 3 rows are there for training and 3 rows can be there for testing. Ideally the recommended way is you keep 75 to 80% of your data for training and remaining 20 to 25% data for your testing purpose. Okay, so now I am setting it at 0.2, which is like 20% of the data. So 4 rows will be there in training. If I just now look at testing, you'll see we have 2 rows only in testing, right? And if we look at similarly Y train, I mean corresponding label for each of them, which is like this thing. I mean four entries for first 4 rows, and Y test will be similarly the last 2 rows. Okay. Now if we want to do this scoring, right? Now actually how we do in machine learning is we never do this X comma Y, right? We always do on train and test, right? So there are 2 scores that you will get. So if we do X train and Y train, I will get training accuracy. So sorry, why is it as minus? Okay, it is coming as minus. Okay, because it has not learned on this training data now. So it was learned on the whole data. So I'll relearn this model. So I will relearn this model on training data. So how you actually do is you don't pass X here, you pass train and Y train here. Learn this. So this is the model. You see the score is 1.0, which is the best score, right? Now this is your training accuracy. How do you want to check whether the model is actually good or not on test? Because training accuracy actually doesn't give you a very good indication on whether the model is good or not. What gives you a good indication is whether this X text comma Y test, if this score is good, then you know that the model is good, right? This score will come out to be low. Why this will come as low is because the model has not seen this data and we have very few data points. Usually in machine learning we don't have like 6 data points, right? We have more data points. So on this you will see the score will come out as very low or a negative score. Negative score means that a bad score. Okay. So what it is saying is that this model is not properly learned. It is fine. The model is not properly learned. Why it is not properly learned is because of limited data. I mean, very few data. Now, another way how you can improve it is because we gave it sequential data for training, right? Let us shuffle this and see if the model accuracy is improving or not. I'll shuffle, I'll change the training and testing data, it will change a little bit. I'll relearn the model. Now let us look at the score. It is still 1. Testing, it is still poor because it's primarily because of the less amount of data that we have. Or let us say if we can increase it a little bit to, let's say 0.4, increase the test data. Training, we are further reducing this thing, so it will be more. So now this has become better, primarily because because we are shuffling now. So this will depend on the kind of shuffle that we have. It's a random shuffle, right? So if it is getting a very good sample space on which it is learning, and because you see now it's a 3200, 4000 and 3600. Now in the test what we have 2600, 3000 and 4100. It is very close to the training data set. So if your test data set is very similar to the training data set, the score will be high. Now if I make it, let's say I do it 50%, right? So it will be the same data set only, so it will be 50%. Let's say I do it 80% for testing, okay, only one data for training. Here you will see test score, training score again will be not enough values, I think. So R2 score is not well defined with less than 2 samples. So because we have reduced the training to far below, it's like only one sample we have in training, so it goes haywire. Okay, let us try with last one attempt. We'll use 0.1% of your data for training. We have 5 data points for training and now only 1 data point for testing. Okay. So you see the training score is 0.98 and the testing score, okay, testing score is also not defined for less modules. Okay, anyways, this is a very small data set. On this you cannot expect to get a very good model, right? But the idea is this. I mean, generally this is how we do. We get your data, we split it into 2 parts, train and test, and the ideal combination is test size as 0.2 or 0.25. Shuffle is usually preferred to be set as true because your data should be shuffled always. And once you have this training and testing data, you call the fit function, pass the training models only, and score. This score that you get by passing train is your training accuracy. The score that you will get by passing test is your testing accuracy. Okay, and testing accuracy is actually more important. Training accuracy is not that important. Okay. So here we are getting a bad number. That is fine. That is absolutely fine because we have less number of data. In general, real practice, we'll have a lot more data because let us take a Boston data set. Okay, Boston data set that I showed you in feature engineering. Boston data sets scalar. So let's take this one. So here you will see it will be much better because the data quantity is much higher. So if we look at Boston, okay, so what is happening here? Oh, sorry, spelling. No. Load Boston has been removed from scikit-learn since 1.2. Okay, scikit, okay. Okay. Scikit-learn Scikit-learn datasets. Boston, they have deprecated. If there is anything else, induced diabetes, low diabetes should work. Let me try this one if this works. Yes, this one is fine. So again, we have some target variables. We have this data. So if I do Boston.date, I mean this actually not Boston. This is diabetes now. So diabetes. So if I do diabetes.data, this will give me X. Okay. So your X is diabetes.data. If I just print X, so this is what your X looks like, right? Now, if we look at diabetes simply, there are many things within diabetes, right? So there is data which is actually your training data. This is your target. Target is your as I told you, many names for Y variable. It is called a dependent variable or target variable. So the target variable. If I do what I need to do is if I say Y equal to diabetes dot target. Okay, now this is your Y value. If I print Y, this is what Y looks like. This is Y, this is X. Now we have X and Y. Okay, we will apply the same thing, same rule, right? So I just copy code from here. X and Y is already there. I will run this. Now if you see X train, it looks like this. So if we do X dot shape, X train dot shape, it is 350 comma 10, right? 353 comma 10. If you do X dot shape, you will see 442. So 442 is there in the actual data set, but in training we have only 353. Where again the other is in test actually, because the remaining are in test. See, here is 89. So 89 plus 353 is like 442, right? So now we have split the data into train and test. Next job is to run the fit function, right? Running a linear regression, and linear regression of course is not that powerful, you know. I mean, there are other better models. This is a starting point only. Now once this regression is done, we will do same regression score. You see the score is like 0.52, not that great. Okay, but still it is okay. I mean, because not that great, it is primarily because it's a linear regression model, and that is fine. I think 0.52 is okay. If you use this, you'll see the same problem we'll again do using decision tree and all. You'll see how we can get much better results with that. But still, you will see that at least the training I'm not testing, I'm not expecting it to be negative with some value. So it is 0.45. Okay. So this is 0.52. Testing will always be little less than training, but at least it is not negative. Okay. And what you can do here is play around a little bit. I mean, I will say, okay, I want maybe less data in testing. I want 0.1 of the data. So in testing, I have only 45 rows. I'm giving more data to training, so that with the hope that maybe my score will increase. But the score is actually not increasing. But these are things that we have to try. But at least the test score is improved, right? So I mean, essentially, if you are getting a model with where the score is like 0.5, 0.6, so those are not good models. Those are not good models in the sense that uh, there may be some other algorithm that you should try. I mean, ideally, a good model is when you have at least 0.8. So we'll see with decision tree and all how you can, or maybe I will just show you quickly also using decision tree. But we will revisit this again. Decision tree scalar. I think decision tree should do a good job here. Let's see. Decision tree classifier. I need decision tree regression. tree regressor. Decision tree regressor. I'll take this one. So here where I'm using this, I will use this instead of reg. I will set reg equal to decision tree regressor. Okay. Again same data. Let me make it 0.2 only, 0.2 because it's a good number. 0.2 is actually what one should use. So now we have a decision tree regressor that is learned. Let us see if the score is, see, score is 1, right?
Yeah.
See, this score is like in bad because it is overfitting on, this is called overfitting.
Correct.
So when you're training, it is learning well, but on the testing, when the results are bad, this is overfitting. So this model is actually overfitting. Now, what you can do is you can reduce the number of training data. Let's try if this is working. No, it is not improving. So this is overfitting case. So what we need to do is how to solve decision tree overfitting cases using random forest. Random forest actually solves this thing. Random forest regressor. Let's see whether this helps. Other options are there. You can tweak around those hyperparameters within decision trees and all. Those also we'll have to see whether that will work or not. Random forest, scikit-learn ensemble. Max depth, random step, fit ensemble, regression. Okay. Max depth equal to 2. Okay. Let us try this now. Hopefully this will improve. What is the default max depth of this? Max depth default is none. Let us try with none and then we'll see if this does not improve. Okay. Now again let me. Okay, this is done. Let me run this. See, it is better. 0.92, not overfitting. This is also better, but still we have to work on some parameters. Max depth equal to 2. This is reducing max depth to increase. To try different values, combinations of hyperparameters and see which one. This is improving gradually. Still, yeah, this is improving, but test data is not good. Nah, this is not cool. We have to figure out something. I mean, we'll take this one offline and see which model is actually doing better. So these are experiments essentially. These, you don't know which model will do best. You have to try all these models and see which one is better. Within the model also there are different hyperparameter combinations that you have to try. What are hyperparameters? Are all these parameters that you see here, like n estimators, criterion, max depth, mean samples. So these are all parameters of that model which you need to change and try out. So these, I mean, machine learning problems are like this only. You have to keep on trying and see which one works the best. So there are certain approaches, I will tell you, but I think this is beyond the scope of, because we have some limited time. Otherwise, there are standard approaches what you need to follow, how to improve your model. I mean, let's say we started with linear regression, it doesn't work. What model should I try next? I mean, before trying a next model, should I do some parameter tweaking to see what is the best I am getting before going to the next model or not? And sometimes these models, I mean, these models that you are working on are classical models, right? Like support vector machines, decision trees, linear regression. These are classical models. They may not solve all the problems, and that is why deep learning came into picture, right? Otherwise, if it was solving all the problems, why is deep learning required, right? So we'll see. We will again revisit this diabetes, and when we look at when we have learned out about other regression models and all, and we'll apply all of them and see which one is doing best. right? Uh, so for the timing, what we learned is basics of supervised learning, uh, using single variable, using multiple variable, using linear regression. Uh, we looked at how you can split your data into training and testing, how you can compute training and testing scores. Detail. We will also talk about this course in detail later on in terms of what are the other scores, right? So right now what we are saying, the score function is actually returning you the R2 score. There are other scores like mean square error, root mean square error,
Yeah.
classification accuracy, and other things. So those things also we will cover later on. Uh, so
Huh.
so this is what was planned for today, and we will talk about other regression models specifically uh, on regression next session, and then we will move to classification. Okay.
Okay.
Yeah. So that is all, and I think we are slightly above time. Maybe what we will do is whatever doubts you have in the previous class, plus whatever doubts you have in this class, will you can collate them
Yeah.
together, and then the next class we'll start with those doubts, and then we'll look at other regression problems. Okay.
Yes, sounds good.
Okay. Thank you.